Hi everyone, I'm Felix Marsh-Wakefield, and today I'm going to be talking about how we transform our cytometry data. In flow and mass cytometry, our raw data are measured as signal intensities, often spanning several orders of magnitude. This means most markers are highly skewed, with lots of low values and a long tail of high values. When we look at raw data on a linear scale, biologically meaningful structures get squashed into a tiny corner of the plot. In this example, there are a handful of cells with very high signal intensity. Even when we adjust the axes, it's difficult to differentiate between meaningful populations. The purpose of data transformation is to rescale intensities so we can actually see and interpret cell populations. To better visualize cytometry data, we typically change how the axes are scaled. A log scale can reveal some populations by compressing high-intensity values, but compensated flow cytometry data often include 0 and negative values. These cannot be displayed on a log scale, causing data to pile up against the axes. For this reason, bi-exponential scaling is commonly used. This retains a linear scale around 0, while transforming to a log-like scale for high intensities, allowing us to visualize the full dynamic range of the data. Most commercial software apply this automatically, which is why we rarely inspect cytometry data on a purely linear scale. So we can adjust the level of scaling. Here we can see how changing the width basis alters how values spread around 0 on the plot. When we increase the width basis, we can see the 10 to the 3 values being squashed closer to 0, essentially compressing the cells around 0. We can see how different levels of scaling can impact how the data look. The levels can influence how many populations we may identify, and this is particularly important when using computational approaches. By adjusting the width basis, we control for this, particularly around 0. The exact values used will be dependent on the experiment, so flow versus mass cytometry, the fluorochrome or metal used, as well as the marker itself. For these reasons, the plots should always be checked. The same scale should also be used for the same marker across samples within a given experiment to maintain fair comparisons. Once we've optimized the scaling parameters for visualization, the final step is to apply a data transformation to the signal intensities themselves. In cytometry, these transformations rescale the data so that values close to 0 remain approximately linear, while higher intensities are compressed in a logarithmic-like manner. Two commonly used approaches are bi-exponential, which is widely used in flow cytometry software, and arcsinh, which is commonly used in high-dimensional and computational workflows. Both approaches produce very similar representations of the data, allowing us to clearly visualize cell populations across a wide dynamic range. The choice of transformation depends on the workflow, but the most important principle is to apply the same transformation consistently across samples and markers. Once transformed, these values can then be used for a wide range of downstream analyses, including manual gating, clustering, dimensionality reduction, and calculating summary statistics such as MFIs. If you're interested in finding out more about this, please check out our Spectre website, a link in the description below, as well as Tom's paper here. So I hope I've given you a better understanding of data transformation and how it's not nearly as painful as it looks.